Welcome to this module on failure and resiliency fundamentals. In the high-stakes world of AI training, network reliability isn't just about uptime, it's about performance. We will explore why detecting failures fast is critical for AI workloads. Traditional data centers, if a web page loads slowly, it's an annoyance. In an AI data center, it's a disaster. AI training is a distributed computing problem where thousands of GPUs act as a single supercomputer. These processes are tightly coupled. If one network link fails or stalls, every other GPU in the cluster waits for it. This dependency makes tail latency the time it takes for the slowest packet to arrive the defining metric for performance. Single network failure doesn't just drop a packet, it idles expensive infrastructure and delays the entire training job. This flowchart illustrates the impact of a single failure. We start an AI training iteration where the workload is distributed across multiple GPUs. GPUs 1 and 2 finish their compute tasks quickly and move to the wait for sync state. However, GPU 3 hits a network delay or failure. Because the workload is tightly coupled, the entire system enters a stall. This results in GPU idle time across the board, leading to significant performance degradation for the entire job. To combat these failures, we cannot rely on legacy tools like SNMP polling, which might miss short-lived microbursts entirely. We need real-time visibility. This is where what just happened, or WJH, comes in. WJH is an ASIC-level telemetry feature that inspects packets at line rate. Instead of waiting to be asked, the switch actively streams alerts the moment a drop occurs, whether it's a physical layer cable issue, buffer overflow due to congestion, or an ACL configuration error. WJH captures the packet header and the specific reason, reducing the time to root cause from hours to seconds. Here we see the difference between streaming and polling. High-volume AI data enters the ASIC. When the ASIC detects a drop, say from a full buffer, it immediately sends the event and header info to the WJH agent. The agent then streams an instant alert to the admin console. Notice the note at the bottom. A traditional SNMP poll would occur much later, likely missing the event entirely or reporting it long after the AI job has stalled. Action is only half the battle. The network must also react. AI workloads generate massive elephant flows that can collide on static paths, causing congestion. We solve this with adaptive routing. Unlike static hashing, adaptive routing monitors queue occupancy and port utilization to dynamically steer traffic away from congestion and failed links. To further enhance resiliency, we use bidirectional forwarding detection, or BFD. BFD provides sub-second failure detection, allowing routing protocols like BGP to converge rapidly and reroute traffic around faults before applications time out. This diagram shows adaptive routing in action. The switch receives data from a source GPU. It evaluates 3 paths. Link 1 is congested, and Link 3 has failed detected instantly by BFD. The switch automatically selects Link 2, which is free. This adaptive route ensures the data reaches the destination with minimal latency, bypassing the bottlenecks and failures that would otherwise disrupt the workload. Finally, we bring all this data together in NVIDIA NetQ. NetQ is a modern operations toolset that aggregates the streaming telemetry from WJH and other sensors. It provides a centralized dashboard where you can visualize flow latency and buffer occupancy across your entire fabric. Instead of hunting through logs on individual switches, Q allows you to correlate events like a configuration change leading to a performance drop and analyze historical trends. This holistic visibility transforms network operations from reactive troubleshooting to proactive optimization. The flow of information starts at the infrastructure layer, with switch 1, 2, and 3 streaming WJH and telemetry data. This data is collected by the NetQ agent and sent via gRPC to the NetQ server. The server processes this into a dashboard, unlocking powerful capabilities: latency analysis to find slow spots, root cause identification for errors, and historical trends to predict future issues.